All right, so we're going to have to talk about probability. I've been trying to warn everyone that this comes about eventually. Um, so I'm going to start with what's classical probability. And that comes from a prediction that you take, and we're going to say the probability of an event. Now, this is not like function notation. What goes in here is not a number, it's a label for the event. And what goes in there does not generate or a mathematical formula like a function. But what it does is it tells us the probability of an event. It's a label. And we'll see this as we develop the notation. And so in classical probability, it's the number of outcomes in the event divided by the number of outcomes in the sample space. So, for example, there are 52 cards in a deck of cards. That's the number of outcomes in my sample space. Drawing a king, an individual king, sorry, not an ace, a king on the first draw. Well, the probability, and I'm going to say probability of a king on the first draw. And just to show how this notation is used, I'm using a symbol to represent the event. And so I'm saying the event is the king on the first draw. So I think I'll put a code for my symbol over here. So we'll say king on first draw, right? Drawing a king on first draw, right? That's what this symbol is going to be. Well, there are 4 kings in the deck, so there's 4 possible outcomes, right? A king of hearts, king of spades, a king of diamonds, a king of clubs, out of my 52. Which means, what is that? That's 1 out of 13. Or we can talk about it, I guess, in percentage terms. I'm jumping over on the calculator here, and this is 0.0769, so on and so on. Just to keep it easy, I'll say, hey, this is approximately 0.077 or 8.7%. Not 8.7%, 7.7%. Sorry. And you'll find, I've warned you this with frequency distributions, that when I see 2 decimal places, I'll tend to call this as percentage. We will do most of our probabilities with these things, with the actual ratios that come out of them, or the decimal version that come out of them. And so we have a probability. It's the chance that something happens. And it's classical because it's based off of the theory itself. Let's look at another one here. Change color again. And we'll go to dice. And I'll look at a couple different things that can come out of the dice. So I'm going to have a D6. There's 6 sides to it. So my sample space is 1, 2, 3, 4, 5, 6. And I could have an event that is, we'll say, rolling a 3. We'll roll a 3. Could have another event, so I'll name that event 1. I'll name this event 2 of rolling a 7. And I could say event 3, roll less than 5. And so the probability of event 1, well, there's only 1 3, so the number of outcomes is 1, and my sample space has 6 things. And that's approximately 0.167, right? It's 0.1666 repeating, but we'll round it, about 16.7%. But we'll write it this way. And my probability for event 2, we're rolling a 7. There are 0 outcomes in that event. Never going to roll a 7. So that's 0. And then the probability of event 3, rolling less than 5, well, that's 1, 2, 3, 4, so there are 4 options there. And that gives me 2/3, or 0.667, or 66.7%. And so probabilities give a rate of talking about the frequency something might happen, theoretically. Now notice I've brought an old friend back, the word frequency. And that gives us our other form of probability. And this is called empirical probability. Empirical probability. And the empirical probability is based off the observations. And the equation for it is the empirical probability of an event is the frequency of the event over the total frequency. Hey, look! That's a relative frequency from our observations. When we observe things, we're actually building a probability. We're looking at, hey, I observed this. This is how often I saw this out of my total number of observations. And if we do things randomly, we can start talking about this as being a probability. And let's look here. Yeah, I want to use the age distribution from the slides. I like this one, and I will come back to it, I think, in a couple clicks. So we'll go back to it. So I have ran an experiment of 975 social networking site users have been surveyed. And we look at their age and how many people of that age came about. So we have age 18 to 22, right? Legal reasons, didn't get anyone over 18 or under 18, right? Legally. 23 to 35, 36 to 49, 50 to 64, and 65 plus, right? Retirees. And so that was the age. And then there was the frequency. There's 156 people, 312 people, 254, 195, and 58. Now, if we sum up all of these frequencies, the sum of the frequencies, there were 975 people, which is what our N was, right? Now, when we did our survey, we said, we looked at 975 people. And so what we want to go is, hey, how many, what's the chance? If I randomly grab into these people, I'm going to get someone between 23 to 35. So I have my 979 people and I'm reaching in and I pull one out. Hey, Rocky, watch me. Let me pull a rabbit out of my hat. No. And so the probability would be, well, what's the frequency? 23 to 35. Well, it's 312 out of 975. Or 0.32. I have a 32% chance of pulling out someone 23 to 35. Well, what could happen if we do our measuring right, if we do our statistics right, this could represent a population. This sample could talk about the population, and then these probabilities might tell me something about the population. And that is part of the game we've been playing. We've observed something, and we notice the frequency it's been happening and the relative frequency it's happened, because we might want to talk about something bigger than what we could observe. And so we have to look at theoretical probability and empirical probability. What ends up happening to make this work is the law of large numbers, which says that the more data I take, the more experiments I run, the probability empirically approaches the theoretical. Now, randomness is weird. I can flip a coin over and 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 over again. And sometimes I'll get tails, 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 heads, tails, tails, heads. And we might look at this as people, because we're hunting for patterns, and go, that's not a fair coin. But random's odd. I've done it. I've flipped coins. I've gotten the same thing over more than I thought possible. In fact, there is a version of statistics called forensic statistics that when people fudge books and fudge numbers, we tend to want to see patterns. And so when we see a pattern in a book, we will artificially make it random. And it usually leaves a telltale sign. True randomness is ugly. And ugly in the way that sometimes it's completely chaotic and sometimes we think there's a pattern there. That's why we have to be careful on how we observe things, because we as people want to find patterns. We have to measure our data very well and measure the randomness that we're expecting to see very well so that the pattern wasn't our wish and our want, but it's actually in the data. And so to do that, we have to study randomness. And so this law of large numbers goes like this, right? So if this is heads and this is tails, and this is the relative frequency of this, well, as I start this experiment, it's 100% tails. And then I get one heads, and then I get a couple more tails, and I get another head. But eventually over time, and I do enough of these, it'll bounce, and it'll start to bounce around being perfectly fair. And usually it doesn't come back up this high, and it will bounce. And it oscillates around the 50-50, which is the theoretical point of the coin. The coin has a theoretical probability of 50-50. And we see this play out over and over again. It still doesn't mean occasionally you can run one trial and you get a rare event, right? And this is why we say run more and more data. The more data you have, the closer you get to the law of large numbers, and you get those unlucky odd bits that come out. All right, the book talks about a third type of probability, and it's called subjective probability. And subjective probability is why this course exists and what's happening. And I've been asking all my classes, hey, how many people have been to a doctor lately? And more people are saying, no, I've actually seen a nurse practitioner. And what has happened is doctors are kind of like House on the television show. And you would come in with symptoms, and they would go, well, I've studied this a lot, and it's most likely you have a bacterial infection. So I'll give you an antibiotic, and you should get better. And then if you don't, they go, well, the next likely thing is you have this. And they proceed to move on and on. We'll do some tests. And what they do is they work their way through the probabilities that the symptoms you've presented and the treatments that they have work their way through the illness until they get to the really rare things where they have to do different types of tests coming through. And so doctors were statisticians, and they developed that statistics by experience. And what has happened, and I remember talking when I was teaching up at Champlain College to a biomedical professor. What used to be the middle class's great jobs to advance are being killed by technology because technology can do this better. And so when we have a program that has the odds and statistics of all the symptoms presented, nurse practitioners can enter it in, and we can compare that to not all the people that nurse practitioner has seen, but all the people in the country, or all the people that are feeding into that database. And so what's happening is this idea of subjective probability, this intuition, educated guesses, and estimates based off of experience are being replaced by large data. Large data sets are changing this. And what that means is we're going to have to change the way we do things. And one of the reasons you see statistics being offered more and more as the math class in colleges, instead of calculus or algebra, which it was before, was we live in a statistical big data world and we need to comprehend what this means. And we need to navigate it. And I'm trying to teach you the language for that happening. Same thing happened with lawyers. Citibank just killed 250,000 man hours of lawyers with one piece of software. Lawyers used to study, they'd read loads and loads of case law. And so they were really good at going, well, this case is very similar to this other case I've seen before in the case law. Well, now that computers can process natural language, which they couldn't initially, they could just tell you how often a word showed. Now they can actually give you context. Computers got better at reading case law. Right? I have a case that involves these things. The computer's going to say, here's all the cases that involve these things, and here's the ones that are most relevant. I have a friend that works for a major pharmacy company, Walgreens, Rite Aid, CVS, those type of places, who worked in the distribution for it. And he was talking about they're starting to use statistical software R coming through. What used to happen is people used to train, and it was like the rule of 7 years. You'd spend 7 years knowing something inside and out so that you would have the experience to make these subjective probabilities. The future is they're going to go away. That doesn't mean we stop doing these things. Doesn't mean that doctors become unnecessary. It just means they're going to have to change the things they do. And out of that, we will probably get a better end result for humanity. Hopefully. And that's why you're learning this stuff, so that you can navigate that better. All right, I'm going to end this bit here, and then we're going to turn this thing about probability into the beginning of what we can do algebra with. Because what we're going to need to be able to do is we're going to need to take these probabilities and we're going to need to make predictions out of them. And to make predictions out of them, we're going to need some algebra or math.